Hi everyone, welcome to Geeks for Geeks Practice. Can you just confirm that if I am properly audible or not? So that after confirmation I can start the lecture for today. Okay, yeah, thank you Satvik for the confirmation. Let's start with today's question. So let me share my screen. So we are going to discuss the problem of the day that was asked yesterday. Okay, so right now I'm at the Geeks for Geeks practice URL. Okay, I go to problem of the day. Then yesterday, the question asked was count ways to reach the nth stair, right? So let's have a look at it. Right. So this is the question. Now, what we'll do, we'll go to the whiteboard. Okay. We'll go to the whiteboard. We'll look at this question in detail over there, and we'll come back to this portal if required. Okay. If required in the sense, obviously it will be required at the end while we go with the code, right? So let's go to whiteboard. Yeah. So the question says that we need to count ways to reach the nth stair. All right. Let's try to read more, okay, in order to have a better understanding. So there are n stairs. Over here, let's say the n is 4. So let's say there are 4 stairs. A person is standing at the bottom, okay, and wants to reach the top. The person can climb either one stair or 2 stairs at a time. All right. Is the capability of the person like one stair or 2 stairs at a time. What we need to do, we need to count the number of ways the person can reach the top, okay, where order does not matter. All right, we will see what do we mean by order does not matter. Okay, yeah, I hope whole whiteboard is visible, right? Fine. So let's try to understand this question with the help of sample input. Okay, so over here n is 4, right? So let's draw 4 stairs. So these are my 4 stairs, right? Now, how many ways we can reach to the top if we are allowed to take only one step or 2 steps? Let's try to find out that. Okay. So there could be one way that you are climbing 2 stairs, right? Like first you came over here, then you came over here, right? So this is my first way, right? Great. There could be second way that you are climbing one stair every time, right? So this is my second way, right? So we have already seen 2 ways. Now there could be third, like you first climb 2 stairs, okay, then one stair, and then again one stair, right? So this is my third way, right? There could be one more where you climb, let's say first one stair, then 2 stair, then one stair, right? So there's my fourth way, and there could be one more where you are climbing first one stair, then again one stair, then 2 stairs, right? So this is my fifth and the last way. Okay. So for 4 stairs, we have seen 5 different ways. Now, when it says order does not matter, it means that if you observe, we took a way where we climbed first 2 stairs, then one stair, then again one stair, right? Then there was a case where we took first one stair, then 2 stairs, then one stair. Then there was one case where we took first one stair, then one stair, then 2 stairs, right? So if you see over here, just we have rearranged our way of climbing the stairs. So see, order is not important. You just need to figure out all the ways. Okay, all of them are treated as a way. Okay, so I hope the question is clear to you. At least what the question is saying, what we need to find out, what should be the final total count. At least that is clear to you. Yeah, Satvik, permutation and combination is what we can apply if you're doing it manually. But while doing it with the help of a program, we need to think of in terms of some general way, right? That works for all the cases, right? So there are many ways to solve it. We'll try to visualize this with the help of recursion. Okay. Now see, why have I told recursion? Because this question is from one of those categories that helps you visualize recursion, dynamic programming, as well as memoization. Okay, so a whole lot of concepts will be covered with the help of this question, and it's very basic question. Okay, very basic question in that category. Okay, so let's try to visualize this. Okay, what is happening? So let me just clear this area. What I'll do? Yeah. So what I'll do, I'll explain you with the help of three stairs. Okay, the logic. This is my ground level. Okay, this is my ground. This is my first stair, second stair, and third stair. Okay, yeah. Now, see what capabilities do I have? I can climb either one stair or two stairs, right? So let's say I want to reach to this three, and obviously I want to reach, right? I want to reach to this three. So what options I have? Like if I am present over here, then I know that I'll be able to reach three, right? With the help of only one step. Now, if I am at 1, then also I know that I have the capability to reach 3. If I take 2 steps, right? From 1, I can take 2 steps and reach 3. From 2, I can take 1 step and reach 3. But if I am at ground, okay, I don't have any choice to reach 3 because I cannot climb 3 steps. I can climb 1, I can climb 2. If I climb 1, I'm sure that I'm not able to go to 3. If I climb 2, then also I'm sure that I'm not able to go to 3. So for going till 3, okay, if I am at this position or this position, I am sure that I'll be able to reach 3, right? Is this thing clear at least? That if I am at 1 or 2, I'll be able to reach 3. Okay, great. So what do I mean to say is ways to reach 3 will be equal to ways to reach 2 plus ways to reach 1. Because suppose if I have x ways to reach 2, okay, and if I have y ways to reach to 1. So if I have reached to 2 with x ways, I know that all those x ways will be in my answer. Why? Because I have the capability to take one step from 2, right? So all those x steps will also contribute to my answer. Now, if I am at 1, then I know that I have the capability to still reach to 3, right? How? I can take 2 steps, right? So this is what we are going to follow. Like now, if I break it down for 2, what are you going to do? For 2, you can take with ways 1 plus ways 0. When I say 0, I refer to ground. Okay. So basically, this is a bigger problem. Okay, this is a bigger problem which is solved with the answers of smaller sub problems. Okay. Now this smaller sub problem can again be visualized with further smaller problems. This is what I am trying to put in front of you. And how come is this happening? If you are interested in that, let's take an example. Okay, Let's take an example. Let's fully try to understand how we are going to compute the answer for this 3. Okay. Let's have a look at it. Let me just put this aside. Yeah. So I'll be using a recursion tree for that. Okay. Just give me a moment. You will understand everything. So let's say I am at, oh my God, just a second. Yeah. Let's say n is equals to 3. Okay. Now for 3, I know that if I come from n equals to 2 or if I come from n equals to 1, I am able to reach 3. Because if I'm coming from 2, I'll use that one step capability of mine. If I am at 1, I'll use that two-step capability of mine, right? Similarly, I know that I will calculate my answer for 3 with the addition of these two, right? But what about n equals to 2? Again, the same thing. For n equals to 2, I know that if I have my answer for n equals to 1 and if I have my answer for n equals to 0, that is at the ground level, I will be able to reach 2 or from 0 as well as from 1, right? From ground, I will direct take two step. From n equals to 1, that is first, I'll take only single step. Okay. So this will also compute the answer for this too, right? Is this clear till now? Like, see, this is a complex question if you try to think it in a complicated way. But it is very easier if you are able to visualize how recursion is working. I'll again just repeat the most important line that helped me form the solution. The most important line was that if I am at, say, at nth stair, I can reach to that nth stair from n minus 1th stair and n minus 2th stair because I have the capability of climbing one step and two step, right? So whatever are the ways to go till n minus 2th stair and n minus 1th stair, if I add both of them, in this case, I will get the answer for going till nth stair. That's it. As simple as that. Okay, and why I am saying nth every time? Because I'm trying to keep it general. I'm trying to keep it general so that it works for any value of n, right? Okay, great. So let's proceed. Fine. Now see, in recursion, you always need to think of some base case or some solutions which is very obvious and that will help your recursion to stop. Like for how long you will go. If you go further, this will at some point of time turn into negative, right? If you do 1 minus 2, it becomes minus 1, which does not make any sense, right? So what you need to do, you need to frame some base case for you. So what we'll do in this case, if we have n equals to 1, I know that we have only one way that we can reach to first state, that is from ground I will take one step, right? So this will give me 1, right? This will give me 1. Now for n equals to 0, it is I'm already at my ground level, right? So think of it in terms of if I am coming from 3, okay, if I'm coming from 3 and I have drawn my recursion tree that I go from 3 to 2, then let's say I go to 0, okay? So can I say this is one way? Like let me draw, okay, let me draw. I am making you visualize this path, okay? So 3, right? So this is the step 0 to 2, then 2 to 3. That's it. This is what I have drawn. So can I say this is one way? So for whenever we are reducing it to 0, we are also having one way in our output, right? I hope this is making sense. Now for n equals to 2, things are pretty simple. I'll just add both of them and I have the answer as 2, right? Similarly, for n equals to 1, okay, I have already told that answer will be 1. Now let me make you visualize for this 2 as well. What are those two steps? Why we got the answer as 2? One step will be to take one step every time, and other will be to directly climb two steps, right? That's why your answer is 2. Now again for 3, what you'll do, you take answer from this side and this side. 2 plus 1, you give it to 3. Your answer for n equals to 3 is 3. That's it. Now, if you want to visualize what are those three possibilities, Let's have a look at it. So one possibility is already drawn, which is this one. Second possibility could be you first take one step over here, then you take two steps. And third could be you take one step every time, right? Great. So this is how we are trying to develop the solution. So is this clear till now? Yeah, that's a very good question. Why there is one way for zero? Okay, because I tried to explain it in another way. I'll explain it again. Okay, no problem. Just focus. See, when we are at ground, okay, how did we reach till ground? There is a reason we have reached till ground, right? That just focus on this path, which I have drawn with the help of this blue marker. Okay, this path. I have reached till zero, right? From three, I went to two, then two, I straight away went to zero, right? So I have drawn the corresponding diagram for that also. Like I am at three, okay? Then I took one step, so I am at two now. Three, two, one. And to reach this two, what I did, I took a step directly from zero. So if I look at the diagram as well as in the tree from the bottom, okay, from here. So I am at n equals to zero, n equals to zero. I go to two, zero to two, I go to zero to two. Great. From 2 I go to 3, right? So if I don't put n equals to for n equals to 0 1 over here, then we will be missing out this particular count. Okay, but that's not true. We need to consider it, right? Is this clear now? That is the reason I have chosen 1 for this particular path. This is one of the base case. Yeah. So now is it making sense? For one, it's pretty much straightforward. If you want to climb only one step, you are just going to take that step, and that's fine. But for zero, the explanation is little bit different because if you consider it in that way, you will think that you are at ground. Why is there any need to take the step? But that's not the justification for taking one for zero. Okay? Or if you want, you can explain or you can understand one in the similar way I explain it for zero. Like you can draw the figure for this one. Okay, or I'll only draw. Give me a moment. Like if I take it for one, I have three, I have two, then I have one, right? So this one I can reach from ground also, right? So there is one way we are taking one for that. So yeah, for n equals to zero, we mean number of ways to reach zero. Yeah, you can say like that. Okay, like that is the number of ways to reach zero. But see, this is a kind of typical question where if you take it as zero, okay, like in some of the cases, base case is already given to you in the question, okay. But over here, if you go to the portal, okay, if you go to the portal, you will see that you don't have that explanation, okay, what you need to do for when you are at the ground, okay. So in order to understand that, you need to read the question carefully. You need to visualize your sample input and output, okay, and you need to understand what the question wants from you. I totally get your point when you say that it's number of ways to just a second. Yeah, I totally get your point when you say that it's number of ways to reach zero. Okay, because this is a tree and we are trying to generalize stuff, right? So even if you say that it's number of ways to reach zero, so how come you have reached to that zero? You have reached to that zero from some path, right? And in order to justify it more, I will go to the constants of the question, okay. So see, in the question, the constants given to you is n should be at least 1, okay. So you are not at all getting zero as input. Is it making sense? Like, is it ringing some bell? Question itself has says that value of n should be at least 1. Okay, so they are considering that you need to take n as 1. You need to reach at least till first step. Okay, yeah. Okay, great. So let's proceed. Okay. Now, if the recursion tree is clear to you, what we can do is we can start looking at the sub problems what we have computed in the tree. Okay, and yeah, the explanation still remains the same. Like n equals to 0 still means the way how you're going to reach to 0. Okay, like as you said, Satwik, we mean number of ways to reach 0. But as I have showed you the constants, the minimum value of n was 1. So this 0 does not take into account how you are reaching from 0 when you are at 0, right? Because you will be given at least n as 1, right? Fine, fine. So we had a lot of discussion on that. That's great. So number of ways to reach 0 is also 1. Okay, that we deduced after going through the constants and with the help of some sample dry runs. Okay, great. So now if you carefully observe, we are seeing n equals to 1 at two places, over here as well as over here, right? Let me take a bigger input. Okay, then you will see that we are computing same stuff, same calls multiple times. Okay, let me take 5. So for 5, what could be the calls? The calls could be 4 and 3, right? Like this will be n equals to 5, n equals to 4, and n equals to 3. For 4 again, the calls could be n equals to 3 and n equals to 2. For 3, the calls could be n equals to 2 and n equals to 1, right? See what I'm doing. This is nothing but n minus 1. This is n minus 2. This is again n minus 1. This is n minus 2. This is n minus 1. This is n minus 2. What is the n? N is nothing but your immediate parent, right? So if you observe, we have call for 3 over here, we have call for 3 again over here, we have call for 2 over here, we have call for 2 again over here, right? So what we are doing, we are computing same thing again and again, which is not required. Like if you can obviously do, but if you try to do it and submit it in the portal right now, you will get time limit exceeded. Okay. So what we need to do, we need to somehow find out a way where we can store these values. Store these values at the very first time they are computed. Okay. So there the help of memorization will come. Okay, where we are going to store the values once they are computed, and in future we are going to use the stored values. All right. So like this is it in terms of improving the time complexity. I will talk about improvisation of space complexity also, okay, at later point of time in today's lecture. But this is it about improvising of time complexity. All right. So let's see how can we do that. What we can do is let's say n equals to 5, right? So we will see what is changing. If you see over here, only n is changing, right, in every call. Like I have seen students getting confused what approach for memorization needs to be taken. Okay, what approach in the sense you will find questions where you need to store stuff. Okay, but students get confused what to store and how to store. Okay, so basically, at that point of time, you need to look at the thing which is changing. Okay, so over here, n is changing. So only one dimensional array is sufficient. Okay, at some places, you will see that two, three things are changing. So accordingly, you need to decide the dimension of your array. Okay, so what we will do over here, we will take an array with size n plus 1. Now you might ask why n plus 1, why not n? It is because indexing is 1 less than your current position. Okay, So if I need to return the ways to reach the fifth stair, I'm going to return the answer present at this position. Okay. So in order to make it 5, I need to take a length of 6, right? Because indexing starts from 0. Okay. Now, now let's see how we can fill this. Okay. So what we'll do, we will initialize all of this with -1. Now you might have a doubt why -1, why it's required. Means what's the purpose of putting -1? See, we are going to check this one-dimensional array every time before doing any recursive call again. Okay. Now, if we are checking, what we will check? There should be something, right? So if -1 is present, that means we have not yet computed the answer for that particular place. So we can go for a call. But if some other value is present, okay, some positive value, okay, then what we can do? Then we can go for then we can go for straight away returning. No need to do the call because already I have some non-zero value, right? That means it is computed in the past. Is this making sense? Like how we are trying to avoid the recursive calls? Okay, fine. Like if you have any doubts till now, you can ask me in the comment section. Okay. So now what we can do is without wasting any time, let's go to the code and try to see different approaches, okay, to solve it. Like I will show you 3 approaches today, okay. So like all of them will be nearly similar. Don't worry about it. Like one will be in C++ and two in Java. You can interchangeably use languages. Okay, no issues with that. Okay, so you're not clear with -1 part. No problem. I'll explain. I'll explain. Let me draw this tree once again. Okay, or let it be like this. I'll just zoom it out. Just a second. Yeah. So what I'm saying is, let's say you have this array. Okay, for n equals to 5, you have this array 0, 1, 2, 3, 4, 5. Let's say you don't have anything in it right now. Okay, in Java, if you take it by default, you get zeros. Okay, but it's fine. We'll come to that. That is language specific. I don't want to talk about language specific right now. Let's go to the tree. You have n equals to 5 passed from your main function. Suppose, okay, if it like there is main function in Java also, right? So after that you are calling for n equals to 4, or let's not talk language specific. Just that you have n equals to 5, you have called for 4, right? Why? Because you know that if you have the answer for 4 and 3, you will get the answer for 5. So right now you have called for 4, okay, and your code is written in such a way that you again call for 3 and it goes on and on and on, right? Until and unless it hits your base case from where it starts returning. Now, my question to you is, if you have n equals to 4, okay, now if you compute it, fine, you have computed it, that's great. You have computed this n equals to 3 also, that's great. At some point of time, you will also compute n equals to 2, right? Now, if you look at this half of your tree, okay, this half of your tree, you are again told to compute n equals to 3. Is it required? Like you have already computed it over here. Like, do you really need to do that work again? I think it should not be done in order to save time. So for that, I'm saying, how will you keep a track? How will you get to know that you have the value stored already or not? For that, I'm saying that I will have -1 over here. Okay, that you'll have -1 over here. Now this will help you. If you have instead of -1 some non-zero value for 3, this will come out to be 3 only. Okay, or let's say let's take it x. Okay. Some non-zero value you have already got it computed, you have stored. Now now when you are at this half of the tree, you are going to compare, is it -1 or is it x or some other non-zero value, something other than -1. If it is something other than -1, then you no need to do further these calls, right? Not required. You will get totally eliminate this part. See, even if it's not clear till now, don't worry. we will see the code, there things will become crystal clear. Okay, then you will be exactly able to visualize, okay, how things are going, how we are checking, and not necessary minus one. In this question, I have used minus one as default initialization because I know that minus one is not a valid output, right? But in some questions, you might get minus one as a valid output. So there you cannot use minus one. You need to use something else. It's just a check, okay? It's just a check that whether I have already computed it or I think or I have not yet computed it. Okay. Okay, yeah, no issues. Yeah, if it's little clear, we will see with the help of code. Okay, even after code, if it's not clear, don't worry. I'll explain everything in detail. Okay, once again, no issues. Let's go to the code now. Okay, yeah. So I'll just maximize this. Yeah. So what I've done is, if you see, I'm now going to show you the first way. Okay. So the first way is something like I have taken a DP array. Okay, of size n plus 1. Let's say n is equals to 5. So I have taken a DP array of size 6. 1, 2, 3, 4, 5, 6. And my objective is that I will finally return the value which I get over here, okay, which says that number of ways to reach till fifth, okay. Now you might again say that why this 0 constant is for n equals to 1, not required. But see, what we will see is if we are at 2, okay, if we are at 2, then we are computing for 0 and for 1, right? Because this is when we take 2 step and this is when we take 1 step. So the answer for this 0 is also required, right? So let's proceed. Now if I go up, I have passed end and DP array, okay? So that's what you see. Now I have straight away checked if n is less than or equals to 1, return 1, okay? So what could be less than equals to 1? Like if n is equals to 1, then also I'm returning 1. If n is equals to 0, then also I'm returning 1. And anything beyond that also, okay? So I hope this is pretty much self-explanatory. Okay, you could have also written separate conditions for n equals to 0 and n equals to 1. Okay, that is also okay. Like if you want, I can do the changes here itself and show it to you. Let's say I don't write this. I write n equals to 1 and return 0, and I write if n equals to 0, then also return 1. Okay, let's say I write this. Okay, so now what I am doing initially, if my n is 5, okay, if my n is 5, I check if my n is 0, no, n is 1, no. dpn not equal to minus 1, is it true? What was the size of my dpn? It was 6, right? 0, 1, 2, 3, 4, 5. So dp5, it is minus 1, right? So this is also not true, so we come to this line. We call on count ways dp in minus 1, okay? So it calls for 4. Again, the same check will be there and all of them will be false because for 4 also I have minus 1. All of them I have minus 1, right? So I call for 3. Again the same check, I call for 2. Again the same check, I call for 1. Once I call for 1, I get it, right? I get it. And I return 1 from here. So I start returning 1 from here. Now once I return 1 from here, what call I get? I get this call. So I call for 0, right? I call for 0. Now if I call for 0, I again get it, right? It is there and I return 1. Now the interesting part comes. You get the answers for both of this, you add them, it comes out to be 2, and you store it in dp2. Okay, so instead of minus 1, you have now 2 over here, right? Now you will appreciate why I have used minus 1 if I go further. If you see over here, now the call will be for 1, right? 2 step. This was all n minus 1 calls. This is an n minus 2 call, right? So when I call for 1, I again return from here, right? I again return from here. For this I have 2. What I do, I add 2 plus 1 and I store it in dp3. So I have 3 stored over here, right? Now if I go further up, see, now you will see the magic of memorization. I have call of 2 over here. I call, I go up, okay? I go up from here. See, how am I going? This was the call for 4, where I'm sorry, the call for 4 minus 1, right? That is call for 3. That is finished, and this is the call for 4 minus 2. That is 2. So now once I go up, okay, I come over here, I see that dp2 is not equals to minus 1. So I straight away return the answer. I straight away return the answer for this. Okay, no need to go for further calls again. See, this is how we are trying to think it. Okay, yeah. So this is a very basic approach of memorization. Okay, like you would have heard of people in interviews getting scared of dynamic programming. Okay, like they are asked to reduce the time complexity, means, but they are somehow get very much scared with that approach. So you can do this. You can write first a recursive solution, then you can just memorize it. Its power is exactly same as a tabular form of dp, okay, because you are using the already stored value. All right. Now, few doubts which you might have: why have I not stored anything at 0 and 1? I would have stored. See, it will not make a difference because anyways I am returning from straight away from here. My objective is not to fill this array for the sake of filling. My objective is to fill this array because I want to save some time. I'm already saving time for 0 and 1, right? So I hope this is clear to you. Okay, let me just clear the screen and run this particular approach. Okay, let's first compile it. Okay, so for 4 I'm getting 5 as the output. Fine. So I'm getting correct answer with this approach. Okay. So now I hope minus 1 is clear, right? Why have I used minus 1? Okay, cool. So now let's go to second approach. Okay. See, second approach is nothing new. Nothing new. I will say it again. Just a smart way to do things what we are already doing. Okay. So in my second approach, what I'm saying is, let me comment out. Okay. Let me comment out this. So anyways, I'm not calling it, but still, like, why to keep this code if I'm not using it? Right, so it is as small as this one, okay? Let me remove this. Yeah, so it is as small as this. Now, what is this? This is just smart way of doing the same thing. See what I have done. I'll show it to you. I have again taken a DP array, okay, of one size greater than, let's say n is 5. So let me take of size 6, okay? So the indexing will be 0, 1, 2, 3, 4, 5. I have initialized 0 and 1 with 1, 1. Okay. And I am running a loop from 2 till less than equals to n. Okay. Less than equals to n means less than equals to 5. So for all of this, what I am doing? Summation of I minus 1 and I minus 2, storing it in I. Yeah, I'm really sorry I have not talked about this modulo, but it's very much simple. Like this question, once I go to the question, you will see that I am asked to give answer in terms of modulo of 10 to the power 9 plus 7. Okay, because if answer is big, it might exceed the range. So if you take the modulo, it is sure that it lies in that range. Okay, that's it. I will show it to you also. Okay, after this explanation, I will show it to you. So yeah. So what I'm doing for DP2, I am adding these two and storing it in DP2. For DP3, again I am adding the two before it and storing it over here. Because that's what my recursion tree was also doing. If you see, for five, I had calls for four and three, and I was just adding, right? Like whatever answer I used to get for n equals to four and n equals to three, right? For 4 again, I was doing, I was going for n equals to 3 and n equals to 2, and I was adding their answers, right? So visualizing this straight away would have been difficult. Like if you backtrack, if you start from the very beginning of today's lesson, you will yourself understand that if I would have showed you this approach in the beginning itself, you would have got confused, right? It would not have made that much sense to you, right? So I hope this is clear now, right? And in the end, all of this will get filled, and we will have our final dpn returned, where n is nothing but we have taken 5 over here. Okay, fine. So I hope this is clear. Yeah, like if there are any questions till now. Okay, so this is my second approach. I'll run it to you and show it. But before that, as I promised, the you are asked to give answer in terms of modulo 10 to the power 9 plus 7. Okay, so that's what I was doing. Let's compile this. Okay, so it get compiled properly. Let's submit it. Right, so you get the correct answer for this as well. Now we have seen two approaches. Okay, now I will talk about decreasing the space complexity. Like if you observe, I think I don't require this much big array. Okay, what I'm trying to say is every time I am only bothered about these two values for calculating the answer for this, right? Like the previous two. Every time I am doing that. Like if someone asks me to calculate for this place, I'm only bothered about this and this, right? So what I can do is there is no need to take this much big array. I can take two variables. I can take two variables where I'll be storing the answers for this and this and calculating the respective answer for this encircled one. Okay, and accordingly I'll keep on changing the values as I go forward in the loop. Okay, this is again improvisation on space complexity. Okay, like I'm not interested in using the entire space. So for that, let's go to the C++ code. Okay, I've not written it over here. Let's go to the C++ code. Okay, so let me just maximize it. See, this is again what I was talking about. So in place of dp0, I am taking a. Okay, in place of dp1, I am taking b. Okay, so a and b is 1. I am running a loop from 2 going till less than equals to n, and in my temp I have a plus b, right? What do I want at the end? If you remember that array approach, what I wanted at the end, if this was 0 1 2 3 4 5, n equals to 5, I wanted this value, right? I'm only bothered about the last value, right? So I want nothing but what is my last value. So if you observe, if you do a dry run of this code, what is happening? Initially your A is 1, B is 1. You have calculated a temp A plus B percent mod. You have initialized this mod with 10 to the power 9 plus 7. Okay. Yeah, I guess it's 10 to the power 9 plus 7. Yeah, it is. So what you're doing, temp is equals to A plus B. So initially temp will be 2. Okay, 1 plus 1. A plus B percent mod. So it becomes 2. Then you are storing the value of b in a. So you are transferring the values. Let's say this is your a, this is your b. Okay, whatever value was there in b, you are transferring it to a. Okay, and whatever value is there in temp, you're transferring it to B. So what is exact actually happening? These two values were required to compute for the answer of this second place. Now, once this answer is computed, you are again shifting the values of the variables. Like you are changing the positions, sorry, not exactly the positions, but transferring the answer. Like this answer will now get stored in B, okay, and this place, this value will get stored in A. So you again have your new A and B, and you calculate answer for this one, right? Is this making sense? So you have escaped from using that much big array, right? So we learned to see how to develop a recursive solution. After that, we saw how can we memorize it, how can we save some time by storing the values which we don't need to compute again and again. Once we saved space, sorry, once we saved time, we saw how to save space, right? So yeah, this is it. Now let me run this solution as well. Okay. If you have any doubts in the explanation, you can ask me in the comment section. Okay. So let's compile this. Okay. Let's submit it. There's some server issue. Let's try submitting it again. Okay. So we get the correct answer, right? See, what I'm trying to say is, in these kind of questions, things will become complex if you do it in terms of permutation combination, or if you go exactly in terms of very detailing. Okay, see, recursion has a trick, I'll tell you. Recursion is how much you can visualize your solution in terms of uh, like smaller solutions. Okay, and don't try to visualize it till the end. First, try to write what you are visualizing, then take a sample input, and then try to visualize. Because if you at first only if you try to visualize till the end, you might get confused as a beginner. Okay, experts do visualize till the end. I am teaching in a way that one how one should start. Okay, how one should start with these kind of solutions. Once you're good with it, you will be able to quickly visualize till the end. Okay, so yeah, this was it for this question. Okay, it's a nice question if you want to see the concepts of saving time, space. Okay, how to convert your recursive solution into a time efficient solution with the help of memorization. And those who have attended my yesterday's live stream, those people can go and practice some more questions which are slightly different but uses stack. Okay, like we discussed next greater element to write, right, in yesterday's class. So you can also have a look at next greater element to left, next smaller element to right, and next smaller element to left, next smaller element to left, right? So I mean all the four variations. Next greater element to right, next greater element to left, next smaller element to right, next smaller element to left. All of them can be solved with the help of stack with slight variations. Okay, and all of them are good questions. Okay then. Thank you for joining Geeks for Geeks practice. We will have live streams after this as well on our channel. So you can stay tuned. All right. See, problem of the day, how it is selected, that see that's what, like, I cannot say to the viewers, right? It's like you people should give the feedback, like is it helping you or not, okay? But yeah, the questions I believe are framed Like it's my opinion that if you do it properly, at least your basics will be good, right? Okay. Yeah, welcome, Satyam. Okay then, this was it for today. Yeah, thank you. All right. Thank you for joining Geeks for Geeks practice, guys. We'll see you tomorrow again with the problem of the day that was asked today. Okay. Thank you.